Okay, there's a classic demo, and it has two cars on a track. They're compressed with a spring and then let go, but they have different masses. And I actually did this experiment for you. I have a demo. Let's see if this video works. If I just switch over here to my computer. So on the left, I have a cart on a frictionless track, and here I have another cart. I want it to be significantly more mass, so I taped in extra stuff on there. And then there is this plunger that I can use on the other side. Actually, I'm looking over here. This plunger right here, I can use that to push them apart. But I'm actually using this little spring right there. So I'm going to push them together with my fingers and let go. And I didn't make any measurements. You could do that if I knew the masses. I put a ruler there so you could get the velocities from video analysis. But I just want to show it to you. So let's see if this works. So push them together, let go. And so you see the most important thing is that one car moves away much faster than the other car. And the question is, how can we calculate the two speeds of the cars based on the masses and also the spring constant, how much is compressed. And I want to build this in Python. That's really what I want to do. So the first step is to get an analytical expression for the velocities of the two carts. So let's go over here to paper and do that, because it's a pretty good problem. Okay, so here I have the two carts. Now, they're going to start off compressed, and that is a spring constant in there. So let's say that they start off with velocity 0, and this spring has a spring constant K equals, I don't know, 20 newtons per meter. I don't even know what it should be. And then S is, let's say, the compression of the two springs. Let's say it's a centimeter. I don't know. We'll figure that out later. And then after I let go, I have this. The two carts, and that one has extra mass on it. And this one's going this way with a velocity, I'll just call it V2, and this one has a velocity V1 in that direction. And if they're the same mass, then they should have the same velocity, but they're not the same masses. Let's start off with, this is a collision problem, kind of. Yeah, it's a collision problem. But let's start off with the work energy principle, and let's say the system of the carts plus the spring. Now, I don't need to include gravitational potential energy because they don't move up and down. That doesn't change. I don't need to include the force from the track because it's perpendicular to the direction of motion. It doesn't do any work. So I can just say work equals 0 is a change in kinetic energy plus a change in spring potential energy. So kinetic energy is going to be 1/2 mv squared, and they both have kinetic energy. And spring potential energy is going to be 1/2 Ks squared, where K is the spring constant and S is the amount they're compressed. So if I put this in over here, I get 0, and the final kinetic energy, they're going to both have kinetic energy, 1/2 m1 v1 squared plus 1/2 m2 v2 squared minus the initial kinetic energy, which is 0, plus the final spring potential energy, which is going to be 0, because now the spring's not compressed at all. So that's 0, minus the initial, so it's going to be minus 1/2 Ks squared. So that's the equation that I have right there. So let's take this and solve for V1. I'm going to solve this for V1. Okay, so first of all, I can multiply everything by 2, and that's gone. 2 times 0 is 2. And then I'm going to move this stuff to the other side. So I get m1 v1 squared equals Ks squared minus m2 v2 squared, right? If I move this to the other side, it becomes negative. That one becomes positive, and I have that. Now I'll just divide by m1, and I get v1 squared is Ks squared minus m2 v2 squared, all of that over m1. Okay, so that's good. Of course, let's just check, right? Even then, I don't think I have to use momentum to show that they have the same velocities. Okay. Yeah, but that's just the energy. Now, in the video, you would need to know the value of that spring constant. You need to know how much it's compressed, but we'll deal with that later. Okay, so now I can look at the momentum principle. Let me write that equation right there because we're going to use that one. V1 squared equals ks squared minus m2 v2 squared, all of that over m1. Okay, so now I can say if if I consider the system of both the carts, then the moment delta p total vector is 0 vector. So that means the initial momentum has to be equal to the final momentum, because this is final minus initial. So now I only have stuff going on in the x direction. So the y direction doesn't matter. So I can say p initial x equals p final x. Okay, so what's the initial momentum is going to be 0, and the final momentum is going to be equal to and this is the x direction, negative m1 v1 plus m2 v2. Right, because this one's going in the negative direction. I do need to consider the direction, and that's that. So then I can solve this for, let's solve this for v1. Do I want to do that? I'm trying to say, let's see, well, so v1, and that's the positive value. I've already taken into account the negative sign there. So v1 is going to be equal to m2 over m1 v2. Now I already know an expression for v1 squared, so I'm actually just going to square both sides of this equation. So I get v1 squared equals m2 squared over m1 squared v2 squared, and then my expression for v2 up here, v1 squared, I can put in. So I get ks squared minus m2 v2 squared over m1 equals m2 squared over m1 squared v2 squared. So now I don't have v1s anymore. I can just solve this for v2. And I do have two terms over here. The first thing I'm going to do is multiply both sides by m1, and I get ks squared minus m2 v2 squared equals m2 squared over m1 v2 squared, right? Because if I multiply this by m1, then I have m1 over m1 squared, so one of those is going to cancel. And this has units of m times velocity squared. This also has m times velocity squared, so that agrees. Okay, so now let's just move this to the other side, add that to the other side, and I get ks squared equals, and I'm going to factor out the v2, v2 squared times m2 plus m2 squared over m1. And if I want, I can get a common denominator here, and I apparently do want. So let's write that as ks squared equals v2 squared times, if I multiply this by m1 over m1, I get m1 m2 plus m2 squared, all of that over m1. And that just makes it a little bit easier to divide. And then from that I get v2 equals, I can just multiply by the reciprocal of this and take the square root. So I get the square root of m1 k s squared, all of that over m1 m2 plus m2 squared. So that's my v2, and then v1 from before, v1 is up here. There. Let me see if that's what I got before. v2 square root, yeah, good, okay. Okay, so now I can use this and to build a model to check. I'm going to check my model, but my model is going to be a numerical model. Okay, so this is what I'm going to do. I'm going to have two carts, and I'll add the track eventually. And this is 1 and this is 2. And this is going to have some spring connecting them, and there's going to be a length of the spring, some natural unstretched length L0. And so if this is a spring of length L0, and then I have a spring that's compressed of a vector length L from the beginning to the end, that's just the easiest way to do it, then the spring force Fs is going to be negative K times the magnitude of L minus L0 times L hat. So in this case, I can calculate that vector length and then find the force on this one pushing that way, F2. And then if I want to find the force on this one, it's just going to be negative F2. It's the same force in the opposite direction. And then if the distance between these gets greater than L0, then the force goes to 0. After that, I can use my normal Euler method numerical model. Okay, and so I'm going to actually model this. So here's the idea. Calculate the force on both carts, which is the same, but opposite. Ignore gravity, ignore the normal force. Use that to find the new momentum. So I'll say P12 equals P11 plus F1 delta t. This is the momentum principle. And then so this is the final momentum for car 1. This is the initial momentum for car 1. And this is over some short time interval. So if I have some short time interval, I can calculate the force, assume it's constant, even though it's not, and then multiply it by this short time interval to find the new momentum. I can do the same thing with the position. I'll call it R12 equals R11 plus P12 over M1 delta t. So this says this is the velocity. Assume the velocity is constant over that time interval, and then just say the final position plus the velocity times time is the new position. And then finally, I can update time. T2 equals T1 plus delta t, and then do it all over. But do it for both carts. And then if they're further apart, then I'll just say there's no force between them. Okay. So I'm actually going to make two carts, and I'm going to use a spring connecting from their centers, even though that's a little weird. It should be on the end, but it'll work out in the end. I think we'll be okay. Because all that matters is the compression. And I'm going to pick some masses and make some carts, and then check it with the equation that I had before. Okay, so let's switch over here to Python. Let me get rid of this. So here I am in GlowScript v Python. I'm going to first put some values in here. Let's say M1 is the cart of the mass of the first cart. Let's say it's 500 grams, 0.5. M2 is, let's say it's 2. And we can change these. Okay. I need the spring constant. I said K equals 20. I need the unstretched length. L0 is going to be, I'm just thinking of the two carts. In my mind, I have the two carts about that far apart. The centers are that far apart. So let's say 0.2, 20, let's say it's 15 centimeters. So 0.15, and then that's that. Okay, so now I'm going to say car 1 is equal to a box. The position is going to be equal to, let's say, 15 centimeters. I said 15 centimeters. So let's make it a little bit shorter. So let's say vector negative 0.07, 0, 0. That's position equals. I got that. Okay. And then the size, and I'm going to make these kind of realistic. I'm thinking about that. What's that? 3 centimeters. So vector, the length is, let's say, I don't know, 0.1, 10 centimeters? Yeah. 0.1, the height is going to be 0.4, and the width is going to be 0.4. And both my carts are green, but I'm going to make one yellow and one cyan. So let's make this one yellow. Color equals color dot cyan. Dot yellow, I'm sorry. Okay, let's run it. Okay, that's a little big, but that's fine. It doesn't matter. I think we can handle that. Okay, so now I'm going to make card 2. Let's just copy this. And this is cyan. And it has the same size. It's going to be in the positive x direction. And it's going to be called card 2. And let's run that. Okay. There are my two cars. I'm pretty happy. Okay, now let's calculate L. L is going to be equal. They also need momentums. So car1 dot p equals m1 times vector 0, 0, 0. Car2 dot p equals m2 times vector 0, 0, 0. L equals vector, no, L is going to be car2 dot pos minus car1 dot pos. So that's the distance between them. And let's print that because let's just make sure that that is a reasonable. So it's 14. I got it right. Okay. So it's compressed 1 centimeter, which seems like a little, but we can change that later. Okay. Let's actually say S equals the mag of, it's going to be magnitude, it's going to be L0 minus the magnitude of L. I'm going to need that to calculate the spring potential energy, so I just want to write that down so I have it right there. Okay, so I have K, I have the mass. I think I'm okay to start calculating stuff. Let's just jump into it. So the first thing I'm going to say is while I need, no. T, is this not big enough? That's good. T equals 0, dt equals 0.001, and I'm going to make a loop while t is less than 1, rate 1,000. So rate 1,000 says don't do more than 1,000 calculations per second. That's kind of important. If I want it to run in real time, that would be the rate. And I'm going to say t equals t plus dt because I forget this sometimes, and then it runs forever. Okay, so the first thing I'm going to do is this. F equals, and this is the force on car2, F equals vector 0, 0, 0. At the beginning of each loop, I'm going to set the force equal to 0. And then I'm going to test if that force, if I need to change that force. Let's see, I'm going to just make sure. Okay, so now the next thing I'm going to do is to calculate L. L equals car2.pos minus car1.pos. I need to recalculate that so I can see if it is indeed greater than L0 or less than L0. So let's say if the magnitude of L is less than L0, then it's compressed and there will be a force. And I can calculate that force. F is going to be negative K times mag L minus L0 times norm L. So norm L is a unit vector in the direction of L. Okay, so that if the compressed more than L0, so the distance is less than L0, then there's a spring force. Otherwise, it's 0. Okay, and it's 0 because I set it to 0 at the beginning of the loop. Okay, so now I can update the momentums. So car2.p equals car2.p plus F times dt. Car1.p equals car1.p minus F times dt. Because remember, if the force of the spring pushes to the right on car2, then it pushes with the same magnitude to the left on car1. Now I can update the position. Car2.pos, car2.pos plus car2.p times dt divided by m2. And I should do this car2.m, but I just want to do it that way. And car1.pos equals car1.pos plus car1.p times dt divided by m1. I think that's it. Let's just see if it runs. I didn't calculate anything. I'm just running it. Okay. Running. I guess it didn't. I guess let's move this in a little bit closer. 6. Now they're starting closer, so it's more compressed. Okay, so I think it's working, right? The car2 is heavier. It's on the right, and it didn't move as much. Let's put that one at something crazy like 20. Let's just see what happens there. Okay, now it's kind of hard to see also because the camera zooms out to fit everything. Here's the easy way to fix that. And this is not the best way. There are camera settings where you can set the angle and stuff like that. But I like to do this. I'll say H1 equals sphere, position equals vector negative 1.500, radius equals 0.001. So that's going to put a sphere over here on the left-hand side, but it's going to be so small you can't see it. And let's put one on the right-hand side. H2 equals sphere position. But it will rescale. Vector 1.500 radius equals, you won't be able to see it, 0.001. Okay, now let's run it. Okay, that's too far away, but I think that does a good job. Okay, let's move this in at 0.7 and 0.7. And again, there are better ways to do this, but I don't like to do things the best way. Okay, I'm pretty happy with that. I'm moving a little bit more. Changes to 0.5, 0.5. Okay, so clearly the yellow one's moving more. It seems like it's working. Now all we have to do is to calculate, print out the velocities, and then calculate the velocities. Okay, so number one, I'm going to print v1 equals, it's going to be equal to car1.p, that's going to be let's do the magnitude. The magnitude of car1.p divided by m1, and that will be in meters per second. And then let's print out v2 equals mag car2.p divided by m2, and that will be in also meters per second. Okay, let's just run that. I don't even know why I'm running this. Okay, so there's my two velocities. Now let's calculate the velocity. Now I'm going to go up here. I'm going to calculate this. I'm looking at my equation over here. Where did I put it? Oh, here it is. Okay, so V2. Let's calculate V2. I'm going to call this V2. I can call it V2 because I didn't use V2. V2 equals the square root of m1 times k times s squared divided by m1 times m2 plus m2 squared. And then I can calculate v1 as just m2 times v2 divided by m1. Now I'm going to put right here, print v1t. This is theoretical velocity. And it'll just be v1 in meters per second. And then down here, I'll do it after this one. Print v2t equals v2 meters per second. Okay, let's see if it works. If it does, then I'm going to add a track and then we'll be done. Okay, that's a win. Same velocities. So if you want, we could even change the masses. Let's just do this real quick. Let's change the mass so that they are the same. We know what the velocity should be in that case. So I'm going to put this one at 0.5 and run it. Then all these velocities should be the same. That's good. You can do things like change the spring constant. You could change the distance between them. You could look at the video, and this would actually be fun. See if you can reproduce this exactly as the video. So know the masses of the things, measure the spring constant. I think I might have my students do this in lab. It'd be a fun lab. Okay, what I want to do, one more thing, is I'm going to add a track, right? Because then it looks just like the thing. So let's say track equals box. My track is actually, I think it's 1.5 meter long. Box. So the position is going to be equal to vector. The x coordinate is going to be 0. But I want to shift it down, right? Because I want to put the track so it's below the two carts. So if I do, the carts have a height of 0.4 or 4 centimeters. So it has to be down 2 centimeters because that's from the center. And then if I make the width of the track 2 centimeters, so it'll be down, so let's say negative 0.03 centimeters. I'm going to move it down. 0. Oops. 0. And then the size is going to be equal to vector 1.5, 0.02, and then how wide is it? It's going to be, the cars are 4 centimeters wide. If I want a little bit wider, I can make it 5 centimeters. So 0.05, that's in the Z direction, which is in and out of the screen. I'm going to leave the color as gray. I think that'll show up. Let's just see if that works. Okay, there you go. Let's make it a little bit wider. So 0.6. I mean, that's pretty good, right? I mean, I've reproduced reality, and this is what we always want to do. If you can reproduce reality, which I didn't actually do because I didn't measure the velocities and the masses and stuff like that, and the spring constant, the stretch, and everything. Yeah, I'm gonna have this. This is gonna be a great lab. I'm gonna make this as a lab. Okay, so there you go. Code down below. I don't think I have anything else to say, but that's that.